Assalamu alaikum student. In this video we will discuss about lab session number 6. The objective of this lab session is to develop a linear model for a DC motor. Basically here we have to develop the Simulink model of the DC motor using MATLAB software. First of all, we have to discuss the block diagram of the DC motor. That will certainly help us in developing the Simulink model of the DC motor. Here is the equivalent model of the DC motor. This DC motor is connected with the mechanical load. This mechanical load has moment of inertia J, the coefficient of viscous friction B, the applied torque by the motor is capital T, and the velocity, angular velocity of the mechanical load is omega. Here is the step-by-step working for developing the block diagram of the DC motor. First of all, we have to write down the equation on the electrical side of this electromechanical system. Vs is the applied voltage, the terminal voltage given to this motor. I is the armature current. R and L are the armature resistance and armature inductance respectively. Vb is the back EMF. Here we go. Simply write down the KVL. Vs is equal to Ri plus Ldi plus Vb. This is the Laplace transformation of the above equation. Solving for the armature current, this would be equal to Vs minus Vb divided by R plus Sl. As we know that the torque developed by the motor can be written as K times phi I. Here K is the machine constant, phi is the flux established by the field winding, I is the armature current. We also assume that the current given to the field winding is constant, therefore the flux is constant. The developed torque expression can be rewritten as K times I. It has dependence only on the armature current. As the supply voltage increases, the armature current also increases. That will increase the torque developed by the motor, or we can say that the motor can also increase its speed. Next is this equation is also numbered as 3 is the useful equation for developing the block diagram. The back EMF is equal to K2 times phi omega. K2 is the machine constant. Again, phi is representing the flux established by the field winding. Omega is the angular velocity by which the machine is running. We assume that the flux of the machine is constant, therefore the back EMF is equal to K times omega, and this is the equation number 5. This equation is also used for developing the block diagram of the DC motor. Okay, next consider the mechanical part of this electromechanical system. We also discuss this topic in the modeling chapter of the feedback control system. We are able to develop its exact mathematical model, and here is the equation for this node, which is representing the displacement of inertial element with respect to the reference point. Okay, in terms of angular velocity, here I have reduced the 1 degree of the equation of the derivative term. Therefore, T is equal to Jd times omega and plus b omega. After taking the Laplace transform, the equation can be written like this. Solving for speed, the angular velocity of the machine, this would be equal to T, the torque developed by the motor, or the torque applied to this mechanical system, divided by B plus S times J. Okay, now we have uh, these equations. Number one, this will be used for developing the mathematical model. The equation 3 will be used, equation number 5, and the equation number 6. These are the equations which will be used to develop the block diagram of the DC motor. In equation number 1, the armature current is equal to the difference of voltage Vs minus Vb divided by R plus Sl. Okay, here is the portrait of equation number 1. This summing point outcome is the difference of voltage, and this difference of voltage divided by R plus Sl. Therefore, the outcome of this block is armature current. Equation number 3 says the torque is equal to K times I. Therefore, this I is multiplied with this block. This block has the transfer function simply K. Therefore, the outcome of this block is capital T, the torque developed by the motor. Till now, we have portrayed equation number 1 and 3. Then use equation number 6. In equation number 6, the output angular velocity is equal to the developed torque by the motor divided by B plus Sj. Okay, here the input to this block is T, and the transfer function of this block is 1 divided by S plus Sj. Therefore, the outcome is omega m. We know that in equation number 5, the back EMF is equal to K times omega. Okay, with this takeoff point, omega m is given to this block having transfer function K. Therefore, the output of this block is Vb. This angular velocity is again passed through the integrator. The block of this transfer function is 1 by S. After this integration process, the final outcome of this block diagram is theta m. And theta m is the angular displacement produced by the motor when the DC voltage Vs is given to this motor. Here is the simplified version of the above block diagram. These two blocks are in series or the cascaded block. Therefore, we can multiply the transfer function of these two blocks. This would be equal to K divided by R plus Sl, and the second block is 1 divided by B plus Sj. These two blocks are also representing the electrical time constant and the mechanical time constant of this machine. This block diagram is used to develop the Simulink model of the DC motor in MATLAB. Okay, now let's move to develop the Simulink model of the DC motor. First of all, we have to realize the block requirement for this model. One block is used to represent the DC source. The second block is required for the summing operation, and these three blocks are required to represent this transfer function, and one block is used to represent the constant gain. Okay, now let's move to develop the Simulink model. First of all, plug in MATLAB, then open Simulink model. In this page, open blank model, then in view option, open the library browser. Here we have number of sections from we are able to select the blocks of our requirement. In this continuous section, we have a block for representing the appropriate transfer function. In this diagram, we need 3 blocks for representing 3 different transfer functions. Okay, add block to the model Untitled. In this Untitled, we have this block. Okay, then Control C and then Control V. The second block, again Control C and Control V. The third block, and we have to connect these blocks. Okay, next is to again Simulink library browser. We have to select a voltage source. Here is the step input, add voltage source. Again, add to the Untitled page. We also has a need of summing operation. Add this one also to the Simulink model. We need a constant gain as well, therefore again this one also in our model. Here is the Untitled. Arrange this thing appropriately. This one is the voltage source. Connect this one. We need 1 plus and 1 minus, therefore change 1 plus sign with minus. Apply and OK. We change the direction of this gain block. We use here Control R. Okay, this one is the correct direction for this block, and we have to connect with this one, and the input is coming from here, as we can see also from our diagram. The input is coming from after the second block. The input is given to this constant block, and the output is output of this constant block is given to the summing block. Okay, here is now next is set the parameters of all individual block. After a step of 1, its final value is 1 and its initial value is 0. Okay, this one is correct. One input is with positive sign, the other input is with negative sign. The transfer function of first block is k divided by r plus sl. Okay, the numerator is, there is no s term, therefore 0 here. The first term is with 0, the second one is constant, the constant is k here. Okay. In the denominator we have r plus sl. Okay, l is the coefficient of s and r with s of power 0. Okay, apply. That's it. This is r plus sl. Similarly, set this block as well. We have 1 over 1 in the numerator, and the first term is the coefficient of s, which is j here, and the next one is b with s of power 0. then apply and 0, and this will be according to our block diagram, 1 plus b plus sj and k divided by r plus sl. Okay, fine. Finally, this block. Okay, here we need an integrator, therefore delete this one. Again, go to library. In this library, in continuous section, we have an integrator. Okay, add to our Untitled, connect this one. The output of this block is omega, and omega after integration is theta m. Okay, we need to display the output. We have to select scopes. Therefore, in sync section we have scopes. We need 2 scopes. Here in this Untitled section, we need these scopes here. We need 1 scope here in order to observe the changes in theta m, and similarly we need also a scope to observe the change in angular velocity. Okay, next is to store the output variable in workspace. This will help out in plotting the graph by using commands. For that purpose, from source section, select block and add block to model Untitled. Next is from sync section, add a block named as to workspace, and also add block to model Untitled. Okay, now go to Untitled. Here is a block. This block is used to store value in workspace. First of all, we use this block to store an array for the angular displacement, and in order to store the array for angular velocity, also connect this block with second one, a time value, a array for time with respect to corresponding these two output. In the workspace we need one more, this block, and connect this one with this as well. Okay, now configure this block as well. Here this block is used to store time small t. Select here the format for the output is array. Next is one more selection, select this one is inherit from input. Okay, do the same for this one as well. You may write here velocity. This block is used to store an array for velocity, suppose v, and once again the format for output is array and inherit from input. Okay, now apply. apply an OK. Same with the case here. This is used for storing displacement. I am writing here displacement. Next is format array, and the next is inherit from output, and simply click OK. This is the Simulink model for the DC motor. Delete this extra clock here, and also calibrate the gain of this gain block, which is K here. Okay, now compare this Simulink model with our required model. One block for VS, and the output from this gain block is VB. The output of this gain block is VB. One voltage source with this summing point with a positive sign, and other one with a negative sign. Same be the case here. Next is the block having a transfer function K divided by R plus SL, is the same here. And the next block is 1 over B plus Sj, 1 over B plus Sj. Then we need a block of integration, same be the case here, a block of integration, and the output of this block is the angular displacement. Before this angular velocity is the before this block of integration, here is the angular velocity, and this angular velocity is given to K. Same be the case here. This angular velocity is given to this block with gain K. After drag and drop the required block and their appropriate connections, I have labeled the diagrams as well. The output of this block is torque, the output of this block is angular velocity, the output of this block is the angular displacement. This scope is used for plotting angular displacement, and this workspace is used to store an array for angular displacement with respect to time. Same be the case here. This block is used to save the angular velocity with respect to time, and this scope is used to plot the angular velocity. Okay, now here we go to run this simulation. After pressing the click button, and when the simulation time is lapsed, this plot is showing the angular displacement, and this scope is showing the angular velocity. Is the output, the steady state output of this DC machine. This one is representing the time constant of this motor, is depending upon the time constant of is depending upon the electrical and mechanical time constant. The most significant is of course the mechanical time constant. Once again, come back to the supporting PDF document of lab 6. In this block diagram, one outcome is theta m and the other one outcome is omega m. The input is Vs. From this diagram, we are able to write down its transfer function using block diagram reduction technique or by using SFG, as we have discussed earlier in video number 23. This one is the output as function of input. Here we can see that these are the two time constant. One is the electrical time constant and other one is the mechanical time constant. Here we assume that the input is a step, therefore its Laplace transformation is Vs by S. If you use the final value theorem in order to find out the steady state output of DC motor with respect to the step input, here we can see that After applying the final value theorem, S approaching to 0, this SL and SJ will be 0. Therefore, we can see that the steady state output has inverse dependence on resistance and the damping coefficient V, and has a direct dependence on the DC voltage. These are the electrical and mechanical time constant. From here it is obvious that if we increase or decrease the value of inductance, that will increase or decrease the electrical time constant. The reverse case is for resistance. By increasing resistance, the time constant will be decreases, and by decreasing resistance, the time constant will be increases. Same will be the case for mechanical time constant. Okay, if you are increasing R, that will reduces the steady state value of the DC motors. Same be the case for the damping coefficient B. If we are going to change L and J, that will not reduces the final value of the DC motor. This is the theoretical case. In real practice, if we are changing L, correspondingly R also changes, because the inherent resistance of the inductor also changes. If we are going to increase inertia J, that will also increases correspondingly the value of V, because as the inertial size changes, the friction from the air or the motor, the load is facing more friction from air, so B also changes. But here mathematically there is no change when L changes or S changes in the final value of the motor. The motor final value only changes when R or B, when R and B are changes. So you have to realize the effect of changing L, R, J and B with respect to time constants, as well as in the final value for the final steady state value of the DC motor. In this diagram, in this waveform, you have to observe the changes in the time constant when you are going to change L, R, B or J. Similarly, the change in the final value. Here in this case, for plotting, I have used these values for the elements of the electromechanical system. These values are given in your lab manual. So in exercise, when you are going to fill up this rows, you have to change different value of inertia, keeping all other parameters as constant, no change in these value, and observe that what would be the change in time constant and what would be the change in final value. Same be the case for all rest of the parameters. Same be the case for these three exercise you have to do. This is all from this lab. Thank you very much. Allah Hafiz.